Hello, Dr. Gonzalez. Today we will be discussing with you the design of the catalytic converter, brought to you by Dylan, Lauren, William, and Kelsey. We'll start off with the introduction and history of how the catalytic converter works and how it was made. Starting off in the Industrial Revolution of the 18th and 19th century, there was a rise in engine-powered process of machines and an increase in emissions and pollutants. It was not until the early 1940s that the air quality in major cities due to smokestacks and car exhaust emissions started to become a concern, which led to the very first catalytic converter. Invented by Eugen Houndy, a mechanical engineer and expert in catalytic oil refinery in 1952, the first catalytic converter was mainly used for smokestacks. At this time, these catalytic converters only converted carbon monoxide and excess hydrocarbons to environmentally safe gases, and with the use of leaded gases, would become clogged due to the catalytic's poisoning and inefficient in a relatively short amount of time. With the introduction of the U.S. Clean Air Act of 1970, which stated that by 1975 all vehicles must cut emissions by 75%, the three-way catalytic converter was invented by Dr. Carl D. Keith, which not only converted carbon monoxide and excess hydrocarbons, but also the equally poisonous nitrogen oxides. In addition to the new catalytic converter, the transmissions from leaded to unleaded gases started, which decreased the catalytic poisoning and clogging of the converters. So, how the catalytic converter works. The catalytic converter takes exhaust gas emitted from the vehicle and through complex catalytic reactions oxidizes and reduces the pollutants to other forms. For example, the main reaction, carbon monoxide to carbon dioxide, which the converter does a 99% conversion of. The methods and assumptions behind our project. The assumptions we used were adiabatic, steady state, negligible pressure drop, Hess's law, reactor fluid is well mixed, and the bed porosity. The reason why we chose some of our assumptions were for the pressure drop, the negligible pressure drop, because we needed a distributed flow to increase our efficiency and conversion of our catalyst. The assumption of the bed porosity to our negligible allowed us to use the design based on a plug flow reactor. The reactions that take place within the catalytic converter. The first reaction that takes place is the nitrogen dioxide to nitrogen and oxygen. And then the second reaction is carbon monoxide to oxygen to form carbon dioxide, and then our hydrocarbon reactions to form water and carbon dioxide. As exhaust gases from the engine enter the catalytic converter, the decomposition of nitrogen dioxide into elemental oxygen plus any excess oxygen from the air intake reacts with the carbon monoxide and excess heptane to form carbon dioxide and water. Alright, so the catalyst data. The activation energy required decreases from our first graph to our second graph, which includes the catalyst. The lower activation energy results in faster reactions, and faster reactions decrease the time of the volume needed for the reactor. These are two graphs we found online. Now the other catalyst data reactor are the platinum and palladium, and those are the two catalysts required for the conversion of carbon monoxide and our hydrocarbons, while rhodium is the catalyst required for the decomposition of nitrogen dioxide. The catalyst is chemically inactive as the engine starts and gradually activates as the temperature of the exhaust gas reaches a temperature of 400 degrees Celsius. So this is the catalyst data density. Found the densities and we found the mass percentages of the catalyst. This is where we came up with our bulk density of the catalyst. We calculated the catalyst density by using weighted average. The bulk density of catalyst will be used to calculate the weight of catalyst needed based on the volume of the reactor.
So now we're going to talk about our energy balance. So the energy balance is as follows, being calculated with these temperature-dependent heat capacities, and here's the total of the heat of reactions. And now we're going to present our rate data. The rate data is shown here to properly describe how the reactions are proceeding. These are the rate constants and how they were calculated. Each reaction rate is of second-order power law calculated by the Arrhenius equation and a temperature-dependent rate constant. This is a representation of the net rates of reaction for the three reactions happening inside the catalytic converter based on the stoichiometry. Now we're going to get into our reactor design. Listed here are the design parameters for this specified catalytic converter. As shown here, 0.25 cubic decimeters would be the best reactor volume necessary to maximize conversion of carbon dioxide and this will operate below the maximum temperature of a converter. We're going to get into some safety concerns and other issues. Some safety concerns should be taken seriously when considering the design of a catalytic converter. It is best to use unleaded gas because leaded gas not only decreases the catalyst efficiency, but also can clog the converter. As a result, the engine could fail due to back pressure. A damaged catalytic converter will lead to exhaust emissions that exceed the EPA required guidelines. Platinum is a precious metal, therefore it is more susceptible to be stolen. Finally, our conclusions. The cost of catalyst should be considered in the design process. In this table, you can see here the average cost per gram of specified catalyst. It costs $45.24 for 1.26 grams of useful catalyst. Increasing the volume of the converter will increase the amount of catalyst needed and therefore increase the conversion. $35 per gram of catalyst is standard to convert the necessary amount of poisonous exhaust gases. The remaining 989.74 grams of catalyst is aluminum, which is very low in cost. Monolith reactors are made of small, long tubes of ceramic that is coated with the same three catalysts. This design allows for smaller physical reactor while increasing the amount of catalyst inside the converter. This style of reactor increases the surface area between the exhaust gases and the catalyst, which increases the diffusion of gases on the catalyst, which increases the reaction rate and conversion. Thank you very much for listening. I'm putting bloopers at the end.
Oh, please, no.
Trust me.
Hello, Dr. Gonzalez. Today we'll be discussing with you the design of a catalytic converter. Why you gotta be...
Take your time. Take your time. It's okay. Okay, we can cut that out too. Just start whenever you want to.
Eugen Houndy. Negligible. The potential energy is greatly increased when we are using a catalytic converter. No, it isn't. It's actually decreased. Let's start that over. Damn, what was that word I couldn't say for the life of me?
Negligible.
I can't say that shit for the life of me. Negligible. Don't you hate that shit?
Now we're going to get into our reactor design.
Reduction. See, now you feel this. Now you feel what I felt. From leaded.
Let me get in my element right now.
Oh, wow. Can I laugh at you like you did to me?
It costs $4,524.
It's not $45,000. It's $45.
Shit.
Yeah, I know. That sounds like $45,000. What the fuck she talking about?
Why didn't you tell me?
I didn't know because you said it, and I was like, what is she talking about? I feel like Kelsey's gonna end up doing this shit later. Bye-bye.